In this video, we are going to discuss conditional trigonometric equations. Remember previously we've been talking about identities and basically formulas that we could use, which are also identities. And those were the types of equations where both sides are identically equal as long as the functions that represent both expressions on each side of the equation were defined. Conditional equations are what we normally think of when we're thinking about solving equations, right? You're going to have at least one solution, but you won't have infinitely many solutions that compose of a big chunk of our real number line. And so remember, conditional equations are equations that are not identity equations, but have at least one solution. What we're going to do is we're going to look at the conditional trigonometric equations, and they're basically two techniques that we're going to use to solve them. And it depends on how many trig functions we see in the actual equation. For trig functions or for equations with one trig function, what we're going to do is we're going to isolate the trig function. Remember, isolate in math when we're talking about equations means to get it on one side of the equation and everything else on the other side. Sort of like this equation here in example 1, part A. We have cosine of alpha isolated on one side, and then we have a constant on the other side, right? What we're going to do is we're going to try to just basically think of what angle theta would equal, what angle equals the given solution. The cosine or the trig function evaluated at whatever angle equals that ratio. That's what we do when we have equations with one trig functions. One trig function. For equations with more than one trig functions, we've got to come up with a way to solve it. Now, you kind of got to be cognizant of the structure of the equation, because sometimes these things look like algebraic expressions or algebraic equations, but they're equations of trig functions, and so it looks a little weird. But we're going to try to rewrite the equation so that it is solvable algebraically. Now, sometimes that means we may have to factor. Sometimes we may have to raise both sides to a power in order to help us solve the trig equation. Sometimes we can use identities after we do all that, or just use identities to simplify the equation to get it to a point where we can either reduce it to equations that only involve one trig function. And we're going to see examples of that. Let's look at the first case first. And so it says, find all real numbers that satisfy the equation. Here we have cosine of alpha equals negative square root of 3 over 2. Notice left-hand side is isolated. We only have one trig function in our equation. Other side is negative square root of 3 over 2, right? So our goal here is basically to find all the angles whose cosine values equal negative square root of 3 over 2. All right, now, one way that we can think about this is we want to solve for our variable. Our variable is in the input of our cosine function. So what we could do is we could take well, I'm going to write it this way. All right. I'm going to write this over here because you don't have to necessarily do this, but this is sort of what's going on in the background. What we could do is we could take the cosine inverse of both sides of this equation. And I'm actually going to do it in the next step so that I can do the cosine inverse of both sides. So I have the cosine inverse of the cosine of alpha equals the cosine inverse of negative square root of 3 over 2. Now, the problem with this method here, right? Well, we know that cosine inverse and cosine, they kind of cancel. But remember that the cosine inverse function has a range that is restricted, right? And so when we use this method here, we are going to get, okay, well, cosine inverse has a range of 0 to pi. So we have to find the angle between 0 and pi that has a cosine value or an x-coordinate on our unit circle of negative square root of 3 over 2. That happens at 5 pi over 6. All right, and so this is the problem with using our cosine inverse function to solve this equation, right? Because this is not the only angle that works. In fact, if I think about my unit circle, alpha can equal not only 5 pi over 6, but it can also equal, in the third quadrant, the cosine of 7 pi over 6 is negative 3 pi over 2, right? And remember that our trig functions are periodic, right? And the period of our cosine function is 2 pi, right? So if I added 2 pi to that, I'm going to get another angle that has its terminal side at 5 pi over 6. All right. If I add 2 pi to 7 pi over 6, I'm going to get the same thing. And then notice I can add another 2 pi to that, right? And so all of my solutions, all of my real numbers that are solutions to this equation here come in the form alpha equals 5 pi over 6 plus 2 pi. And I'm going to put a constant k there where k is an integer to notate, to denote that, hey, I can go around my unit circle and I get back to that terminal side and I'm going to be at an angle that has a cosine value of negative square root of 3 over 2. I can do another one, or I can go counterclockwise, all right, and get back to that same terminal side. The same thing happens for 7 pi over 6. It's going to be 7 pi over 6 plus 2 pi k. And so what we can do is we can say that our solution is consisting of the set of our angles such that, I'm writing this notation, such that alpha equals 5 pi over 6 plus 2 pi k, or alpha equals 7 pi over 6 plus 2 pi k. All right. And this is our solution set. It involves an infinite number of angles, right? Because we're periodic. And just so that you'll see a few of those angles here, I'm going to write 6 angles. Well, yeah, I'm going to have 5. I know it's going to be 5 pi over 6. If I add 2 pi, right? 2 pi with a denominator of 6, I multiply by 6 over 6. That's 12 pi over 6, right? So if I add 12 pi over 6, I'm going to get another angle. So 5 pi over 6 works. We already had that 7 pi over 6. Another angle will be to add 12 pi over 6 to each of these, right? Because that's adding 2 pi, right? So 12 plus 5 is 17, so I get 17 pi over 6. If I add 2 pi to the 7 pi over 6 here, right, where we let k equals 1, we're going to have 7 pi over 6, which is plus 12 pi over 6, or 19 pi over 6. And if we let k equals negative 1, right? So in these two right here, I let k equal 1. I can let k equal negative 1 and get me some negative angles, right? So that means I'll be subtracting 2 pi here. And remember, 2 pi is 12 pi over 6, so we get negative 7 pi over 6. And if I subtract 12 pi over 6 here, I get negative 5 pi over 6. And so these are some specific angles, but this notation here allows us to get all of the angles that are real numbers. And note here that k is an integer. All right, k is an integer. All right. So once it's isolated, you find your angle. You can add your period times k, and you're going to get to another angle. Let's look at another example. Part B, we have square root 3 times the tangent of 3x plus 1 equals 0. We want to solve this equation for x, our variable here, right? Well, when we do that, notice we have one trig function. It's that tangent of 3x. What we're going to do is we're going to isolate that. That means get it on one side by itself. The first thing I'm going to do is I'm going to subtract 1 from both sides. I get square root of 3 times tangent of 3x equals negative 1. And then I can divide both sides by the square root of 3. And I'm going to get tangent of 3x equals negative square root of 3 over 3, right? Now, again, almost like what we did over here, right? We want to isolate the trig function, right? Our cosine of alpha here. That means we need this cosine, we needed that cosine to cancel, so we can take the cosine inverse of both sides, right? And then that would leave us with just our alpha. The problem with that, since this is the inverse function, we're going to be losing one of our solutions. And so that's why I came back over here and I thought about, okay, well, are there any other angles in my unit circle that has this value here? All right. Notice when we did that, we were just left with whatever the input was. All right. My point in saying that here is I want to know the angle on my unit circle that has a y over x, because cotangent equals y over x, that equals negative square root of 3 over 3, which is the exact same thing as negative 1 over the square root of 3. The only way that we're going to get that, remember, tangent is a y over an x, and the only way for us to get 1 over the square root of 3 is for your All right, I'm gonna just put a plus or minus here and a plus or minus here. It's for your y coordinate to equal 1/2 and your x coordinate to equal square root of 3/2, right? Because if I do that, you divide by a fraction, you multiply by its reciprocal. Notice you're going to get that 1 over that square root of 3, right? So we got to know the angle that has a y coordinate of 1/2 and the x coordinate of square root of 3/2, but it has to be negative, right? And that is what 3x is going to equal. Because now it's not an x here because that input is a 3x, right? So if we were to try to do the tangent inverse to kind of cancel that, we would be left with 3x. So this is what 3x equals because we would be doing the tangent inverse, right? But so we have 3x equals the angle that has a y coordinate of 1/2 and an x coordinate of square root of 3. Well, it's going to have a reference angle of pi over 6. And since it's negative, tangent is negative in the second and the fourth quadrant. And so it's going to be 5 pi over 6. Or we get our other solution for letting 3x equals fourth quadrant, 11 pi over 6. Now, what we have to do, because we want to find, now listen to the instructions, find all real numbers. So we're going to have to do this plus k stuff, some multiple of some number. And what we always do is we add the period. Well, if you remember, for a tangent function, its period is pi. All right, so I'm going to add pi k, and I'm going to add pi times k there. Now, this is the solution for 3 times x. If I want to know what x is, which is what we want to solve for, we're going to divide both sides by 3. 3 divided by 3 is 1, so we just get x. Notice, if I divide by 3, I multiply by 1/3. So that'll give me a 5 pi over 18. And in here, when I divide both sides by 3, I made an error. This is 11 pi over 18 plus pi over 3 times k, right? I divide both of these terms. Since that's a plus sign, both of these must get divided by 3, right? So I get 11 pi over 18 plus pi over 3 times k, and I left that off over here, pi over 3 times k, right? Now, something interesting happens with this tangent function, right? If I try to write out some of my solutions, right? For instance, I know I have 5 pi over 18. If I let k equal 1 here, right? If I let k equals 1, notice that pi over 3 is 6 pi over 18 if I got it to the same denominator as this initial 5 pi over 18, right? So if I do that, then my next number after adding the 6 pi over 18 would be 11 pi over 18, which is this exact same number that I have here. All right, and if I added another 6 pi over 18, which is letting k equal 2 here, I'm going to get 17 pi over 18. All right, I want you to notice that. So I let k equal 1, and then I let k equals 2. So this is the value for letting k equals 1. This is the value for letting k equals 2, right? Now, if I start at 11 pi over 18 over here, and I let k equals 1, right? Right? If I let k equals 1, that's the same thing as adding 6 pi over 18, because if I multiply this by 6 and that by 6, I get 6 pi over 18. Notice that when I do that, if I add 6 pi over 18 to 11 pi over 18, I'm going to get 7 pi over 18, right? And so what's happening here is this whole solution here is sort of redundant. I don't need to include that here because it is redundant. By letting my solution set just involve the 5 pi over 18 plus pi over 3 times k, that's the pi over 3 here, times k, I'm taking care of this, so I don't need to write this in my solution set, right? Because I'm going to get all of my solutions. And so my solution set is going to be the set of all x such that x equals 5 pi over 18 plus pi over 3 times k. And here again, k is a constant. It is a real integer. It is an integer. And so this is how we can write our solution set. All right. So notice the instructions here. It was find all real numbers that satisfy the equation, right? In each of these equations, we had one trig function. This was the trig function evaluated at a single angle. And in this example, we had a trig function at evaluated at a multiple of an angle, right? So we had to go that extra step to divide both sides by 3 once we found the angles. Now look at these instructions in this example. It says find all real numbers in the set from 0 to 2 pi, not including 2 pi, that satisfies this equation, right? So I only want the angles that are in my first quadrant, basically. I mean, my one revolution around my unit circle. And so here we have 2 times the cosine squared of x plus cosine of x minus 1, and I equals 0. And I want to solve this equation for x. Remember, x is the input into your trig function, right? But we have multiple trig functions or multiple expressions that involve trig functions, right? So this is different from the last example, right? And just as a review, we're going to use one of these methods here. We're going to try to factor to solve. We're going to try to raise both sides to an exponent to solve, or we may try to use identities to solve, right? And so let's go back here. Notice here, I have a squared term, I have a linear term, and I have a constant. Let's write that down, right? Here, I have, this term right here is squared. This term right here is linear. And this term right here is constant. It almost looks like a quadratic equation, right? For instance, if I have the quadratic equation 2x squared plus x minus 1 equals 0, this is what this looks like, all right? This is exactly what it looks like, but instead of having an x right here, it has a cosine of x in the place of x. It has a cosine of x in the place of x, right? Now, I know that we went through that long method of factoring, right? But we could probably look at this and factor this way, right? We know we're going to put a 1 here and a 1 here. If I factor that this way, notice if I multiply this back out, I'm going to get a 2x squared, right? That'll give me a 2x squared plus 2x minus x, which is that plus x there, and then we'll get that minus 1, right? And so this is the way I factor this, right? So I'm going to apply that to this quadratic trigonometric equation, but I'm going to replace the x with cosine of x. So what I'm going to do here is I'm going to factor this, and this is going to become 2 times the cosine of x minus 1 times the cosine of x plus 1 equals 0. And so we factor that, right? And now that we factor, we have a product of two numbers or two quantities, and the product equals 0. So what I'm going to do is I'm going to set each of those factors equal to 0. And I can solve these equations for x. Here, I'll add 1 and divide by 2. I get cosine of x equals 1/2. Here, I'll subtract 1 from both sides. I get cosine of x equals -1. Now, my goal is to find x. So I got to find the angle between, my solution has to be between 0 and 2 pi. It's missing the bottom part of this thing here. Sure, it's on your paper. But cosine of x equals 1/2. Find the angle between 0 and 2 pi that has an x coordinate of 1/2. Well, that happens at pi over 3. And that also happens at 5 pi over 3. Right? In the first and the fourth quadrant, cosine is positive, and so we get those two solutions there. All right, if I go to this equation here, I want to find the angle on my unit circle that has an x coordinate of -1, and that only occurs at x equals pi. And so my solution set here is pi over 3, pi, and 5 pi over 3. Notice here, I'm not adding the plus 2 pi k here. I'm not adding that because the instructions only wanted me to find all real numbers in this set from 0 to 2 pi. All right, so I don't have to go around my unit circle any further. All right, let's look at an additional example here. Here I have cosine of x minus the square root of 3 equals the cotangent of x. Notice here, and this is something that you want to recognize here. Anytime I see a cosecant and a cotangent in the same equation, I'm going to think about this identity here. Cotangent 1 plus cotangent squared of x equals cosecant squared of x, right? We know this to be true, right? And so notice here, this is an equation that has two trig functions, right? So I'm going to try to factor. I'm going to try to do some other things, but I want to reduce this down to an equation where I don't see two separate trig functions. And by squaring both sides, I can introduce some squares to this equation, right? So that I can ensure that I can use this identity here, right? And so I reduced it to an equation with one variable. And so I'm going to square both sides. Remember, when you square that left-hand side, this is the same thing as cosine of x minus the square root of 3 times the cosine of x minus the square root of 3, right? And that cotangent squared is cotangent squared of x, right? But when I do this, I FOIL it out. I get cosecant squared of x minus 2 square root of 3 cosecant of x, and then that'll be a plus 3 equals cotangent squared of x. Notice here, now it looks like I complicated this a little more, right? But what I gotta make sure of is that I can identify that this is happening here, right? Notice if I were to subtract cotangent squared from both sides, or let me get this cosecant squared of x on the other side, right? So I'm gonna subtract, and I'm gonna actually write this out. I'm gonna subtract cosecant squared of x from both sides. And I get negative 2 square root of 3 cosecant of x plus 3 equals cotangent squared of x minus cosecant squared of x. Now, if I look at this equation here, if I get cotangent and cosecant on one side where I have cotangent squared minus cosecant squared, I can get 1 plus cotangent squared of x minus cosecant squared of x equals 0. Subtract 1 from both sides of this identity, we get negative 1. And so wherever I see a cotangent squared minus cosecant squared, I can replace it with negative 1. Well, if that is the case, then this right-hand side equals negative 1. Now I have an equation with just one single trig function. So the benefit of squaring both sides, which is not a property of equality, so we always have to check our solutions here. But the benefit of doing that is the fact that I could use this identity. And by using that identity, I can get rid of one of the trig functions. And so now I have an equation with just one trig function, right? It takes a little bit of foresight to kind of see that. All right, so I'm going to subtract 3 from both sides so that we can isolate this trig function. Oh my gosh. My doorbell rang. All right, and so when we divide both sides by that, we isolate our cosecant of x function, and we'll end up with 2 over the square root of 3. And so now our goal is to find what angle, again, we're going to be between 0 and 2 pi, right? That has a cosecant value of 2 divided by square root of 3, right? We know that we can simplify that into 2 square root of 3 over 3. But notice this is, cosecant is 1 over y, right? And so the y value would have to be the square root of 3 over 2. And so for us to get that value, we're going to have that x is going to equal, well, a y value of square root of 3 over 2 is going to happen at pi over 3, or it's going to happen at 2 pi over 3 in order for it to be positive, right? And these are our potential solutions, right? And so what we can do, anytime I square both sides, sometimes I will put more solutions that are actual solutions, or end up with more solutions that are actually solutions. And so what I'm going to do is I'm going to check this solution here. I'm going to check and see if I do the cosecant of pi over 3 minus the square root of 3. I want to see if that equals the cotangent of pi over 3. Let's check that out and see. And I'm going to do the same thing for 2 pi over 3, right? this is going to be important, right? So the cosecant of power of 3, again, that was 2 over the square root of 3 minus the square root of 3, right? Over 1. And then the cotangent of power of 3, that's the y, the x over the y. So that's 1/2 divided by square root of 3 over 2. And then the rest is just simplifying, right? If I do 2, that'll be 2 minus 2 square root of 3 over 3. We want to see if that equals 1 over the square root of 3. Now, if you look at that, you will notice that I made a mistake. Right. So when we get a common denominator, that's a 1, right? 2 is not our common denominator, right? And so when we get a common denominator, our denominator has to be the square root of 3 here, right? So I would have to multiply the numerator and the denominator of this by the square root of 3 over the square root of 3, right? And so what we're going to have here is 2 over the square root of 3 minus the square root of 3 times the square root of 3 is 3 over the square root of 3. And if I simplify that, I'm going to get -1 over the square root of 3. And we know that that definitely does not equal positive square root of 3, 1 over the square root of 3, right? And then we can similarly check the solution to 2 power 3, right? So we go back to our original function. We plug in 2 pi over 3. And when we do this again, this is in the second quadrant. Sine and cosecant are positive, so we're going to get that 2 over the square root of 3 minus the square root of 3 again. And then the cotangent of 2 pi over 3 is actually going to equal well, in the second quadrant, cotangent is negative, and so we're going to get a -1/2 over 2 over the square root of 3. So we get a -1 over the square root of 3. Again, we multiply the top and the bottom of this by the square root of 3. We're going to get 2 over the square root of 3 minus 3 over the square root of 3, which we're going to get a -1 over the square root of 3, which definitely does equal -1 over the square root of 3. All right. And so our only solution here is 2 pi over 3. So my solution is 2 pi over 3. So anytime we square both sides, right? Usually we square both sides so that we can use our Pythagorean identity, which usually will allow us to reduce our equation from having 2 trig functions to having only 1 trig function. Once we do that, we'll be good to go, but we always have to remember to check our solutions. All right, sorry for the breaks in between this video, but there we have it. We have our solutions. And just in case you didn't see that last part where I was checking those solutions, there it is, checking the solution of x equals 2 pi over 3, which is the only solution. That concludes this video. I'll see you during the next one.